Hello, good morning students. So today we will discuss a new topic that is about angular momentum of conical pendulum. You must have learned about simple pendulum in your higher secondary classes. Simple pendulum and its period of oscillation and how the resulting equation can be used to find out acceleration due to gravity, etc. You have studied in your plus 2 classes. Here now we will study a new type of pendulum that is called conical pendulum. Okay, so this module has three main topics. First is finding out the period of a conical pendulum, then calculating angular momentum of a conical pendulum, and finally out of the angular momentum we will try to calculate or find out the torque acting on a conical pendulum. Okay, these are the main three sections of this module. So let us begin with first the introductory part of the conical pendulum, in which we will calculate period of a conical pendulum. As you know, a simple pendulum always have a string and a bob, and in a simple pendulum the bob moves in a to and fro path, to and fro path, in fact always in a straight line. But when you come to conical pendulum, in a conical pendulum again it has a string and it has a bob, and the string, one end of the string is fixed at a pivotal point, and the bob traces out a circular path. The bob moves in a circular path periodically. Okay, cyclically the bob moves in a circular path. And as far as the string is concerned, string traces out a conical section. You can see in the graphics given here, the string traces out a cone, a circular cone. That is why conical pendulum is known in that name. Conical, the term conical comes from what type of a geometrical section it traces out. You can see it makes out a cone, a circular cone. So we call it a conical pendulum. So this kind of a conical mechanical system has so many importance in mechanics and physics. We can use this particular system to explain many other physical systems in many areas of physics, for the spin of an electron, for the motion of a charged particle in a magnetic field. Okay, even planetary motions, you can explain many aspects of planetary motion using the concept of conical pendulum. Okay, so that is the relevance of conical pendulum. And as I told you, it consists of a weight or a bob fixed around one end, and other end is suspended with a pivot. Okay, so that is called a conical pendulum, and it moves with a constant speed in a circle. Okay, so you must keep in mind that the bob is always moving with a constant velocity, or you can say with constant angular velocity. So it is moving in a circular path. Okay, and in fact, as I told you, it can be used to describe even the orbital motion of many planets. So that was done by Robert Hooke in 1660, and even in many other physical system we can explain using the concept of conical pendulum. Okay, even precession, when a charged particle is put in a magnetic field, it moves in a circular path. Even describing the precession motion, we can use some of the elementary concept of conical pendulum. Okay, so these are the introductory statements. Now let us come to the first task. We want to calculate the period of oscillation of a conical pendulum. Okay, so we have the pendulum here, and this is the bob, and as you know, it is swinging in a gravitational field. So obviously there will be a force mg acting downward. Here mass you can take as capital M, mg is acting downward, and of course there is a tension, tension is acting along the spring. Okay, and this tension is giving it the necessary centrifugal or centripetal force to circle round in a round path. Okay, so the tension you can resolve along two mutually perpendicular directions. One is T sin theta. The T sin theta is giving it the necessary centrifugal force. Okay, sorry, centripetal force required to move in a circular path. And of course, there is a vertical component, that is T cos theta, which is exactly opposite to mg. So in the equilibrium condition, always mg, downward mg will be equal to T cos theta. What is theta here? Theta is the angle between the vertical line and the string. Okay, it's the angle between vertical line and the string length, that is theta. Okay, so you have some equilibrium equation then. What are the equilibrium equation? Let us see. As I told you, there is a centripetal force that is given by the spring, and you know centripetal force is always expressed by mv square by r. So in this case, v is the velocity of the bob with which it is circulating, and r is the radius of the circular path. And radius will definitely change with the angle theta. Okay, so there is a dependency between r and theta. Okay, and again we have seen that this centripetal force is equal to T sin theta as given in the figure. Okay, now come to if you equate both this relation, we get T sin theta equals mv square by r. So there is no doubt in it. And when we come to the vertical part, that is T cos theta, in the equilibrium condition, T cos theta, the upward component of T cos theta will be equal to downward component of mass mg, where mass is the mass of the bob. Okay, so we have now two relations, one is T sin theta relation, one is T cos theta relation. If you divide simply T sin theta with T cos theta, you get mv square by r by mgr. It's a very simple relation, and by cancelling all the masses, we get sin theta by cos theta equals v square by r. Okay, just you rearrange this equation. When you rearrange this equation, we get g by cos theta equal v square by r sin theta, for v is the velocity with which bob is circulating, and g is the acceleration due to gravity at that place. Okay, and just a rearrangement, we have g by cos theta equals v square by r sin theta. And you know, it is a very interesting equation. This equation is applicable universally, everywhere, not only on the earth. So using this equation, if you have a conical pendulum, if you do a similar experiment in any other planets or satellites or anywhere outside the earth, you can find the acceleration due to gravity existing at that point. You measure velocity of the bob and radius of the circular path traced out by the bob and the theta. You can simply measure or compute the value of acceleration due to gravity. Okay, this has been used by cosmonauts to calculate g, to compute g in many other places. Okay, and here you have a velocity. So this is a velocity with which it is moving in the circular path. So velocity you can write as 2 pi r by t, because you know this is the total length of the circular path. This is the time taken by moving once in a path. So you know velocity equal to distance by time. Okay, 2 pi r by t. So you can insert this 2 pi r by t here. Okay, by removing this v, we get g by cos theta equals 2 pi r by t all square r. A simple substitution, and if you rearrange the equation, we get sin theta upon cos theta into rg upon 2 pi r whole square equals 1 by t square. Again, if you rearrange it, you will get tan theta equals g divided by 2 pi all square r equals 1 by t square. So we get here the period of the bob. Okay, period of revolution of the bob. So we have the t square equals 2 pi all square r by g tan theta. Okay. So once again taking the square root, you get a very compact, beautiful equation for finding the period of oscillation of the bob in the conical pendulum. Okay. And again, if you go to the figure, you can replay this small r. This is small r is the radius of the circular path. From the diagram, you can see sin theta will give you opposite side r by hypotenuse. There is a length of the string. So you can remove the small r from here by substituting L sin theta. Okay, now you can remove the small r part. So we get what we get period equals to 2 pi L sin theta by g tan theta. Okay, so we remove the small r from here by substituting r equal to L sin theta. So obviously this will reduce now to 2 pi into L by g cos theta. It may be worthwhile to remember that for a simple pendulum, the period of oscillation is 2 pi into L by g only, if you neglect the sin theta part. But in a conical pendulum, you can see now we are getting t equals 2 pi into root of L by g cos theta. So within the square root, there is a theta, cos theta part is there. So this is the exact equation for finding the period of oscillation of a conical pendulum. But if you imagine that the angle of inclination is very small, that is, the angle between the vertical line and the string is very small, then cos theta you can imagine as 1. Okay, cos theta will be 1. Then your equation becomes period of oscillation, or period of motion, period of the conical pendulum becomes 2 pi into root of L by g. Okay, exactly we get a identical equation for that of a simple pendulum. Okay, and keep in mind this is applicable when the inclination, angle of inclination is negligibly small. Okay, so keep in mind the actual equation is the first one, which contains the cos theta part, and this is an approximated equation. The final equation is only an approximated equation. So we got the expression for the period of oscillation of a conical pendulum. Okay, it's a very useful relation. One can do so many problems based on the conical pendulum using this equation. Now let us move on to the second part of the session, angular momentum of conical pendulum. As you already know, it is making a circular motion. So definitely there is a contribution from angular momentum. Why it is arising? Because it is moving with reference to a point. Okay, we have a pivotal point, a point of suspension, and another point is the center of the circular path. Okay, because particle is moving in a circular path, so there is a center. That center you can call A. Okay, so with reference to the point A, there is an angular momentum. Okay, and in addition to that, you can see from the diagram, this circular cone has a apex. Okay, the B is the apex point. With respect to B also, the bob has an angular momentum. With respect to B also, bob has an angular momentum. So a conical pendulum has two types of angular momentum. One is with respect to the point A. Okay, other one is the with respect to the point B. Okay, so with respect to the point A, it is due to the rotation. And second one, with respect to B, it is not exactly rotation. There are some other contribution. What is the exact physics of that? We will very shortly discuss. Okay, very shortly discuss. But anyway, you keep in mind that the direction of LA, angular momentum, with respect to A is shown with the red line, red arrow in the diagram. And the remaining things we will be shortly seeing. So let us keep in mind that the total angular momentum of the bob with respect to the point A and B will be equal to vector LA plus vector LB. So the reason obviously I told you. And now let us calculate one by one. What is the angular momentum of the bob with respect to the point A? Okay, so as the bob is moving, so there is a perpendicular distance between the point A and the bob that you can call R perpendicular, okay, or simply as R, small r, radius of the circular path. And there is a momentum tangential to the circular path always. That momentum small p will be equal to mass of the bob times velocity of the bob. Velocity is the linear velocity of the bob. So in the previous topic, we in fact take the mass of the bob of small m. You can imagine it as capital M. Okay, simply change is required. So assume it is also capital M. Okay, so you have now velocity here. Velocity can be written in terms of r and omega. Imagine the angular velocity of the bob is omega. You can replace the velocity with r and omega. So now you have r into m into r omega. Okay, so vectorially if you write it, you can write it as mr square omega into k cap. What is k cap? From the diagram it is obvious that since bob is moving in anti-clockwise direction, obviously the direction of LA will be upward. Will be upward. That is given as k cap. Okay, it is k cap towards upward. Okay. So we got the value of LA. Now what is left? We want to find the value of LB. So that is taken with respect to the point B. So let us imagine a position vector connecting the point B and the bob. Let us take it as r cap or vector r cap, r prime. In fact, it is r prime, vector r prime. And obviously you have the momentum P given here. So angular momentum of the bob with respect to the point B will be vector r prime cross vector P, because of the obvious reason. And vector P you can replace with capital M, okay, and the velocity. So we get this vector r cap is obviously actually the length of the spring. So you can replace magnitude of the angular momentum LB is magnitude alone. By replacing r prime, you can write L times m into v. So there is no problem. Simply replace the r with a small m. Okay, or you can simply write it as by taking velocity as r omega. You can write m L r omega. So there is no problem in writing m L r omega. And again, you can see if you want to write it vectorially, we will have to write it like this. Velocity is here along the direction of momentum, and vector L is like this. So when you take the L cross P, you can see that it will be always directed like this. Depending on the position of the bob, vector LB will be directed like this, like this, like this, like this. That is every time instant LB varies, vector LB varies. At this time instant it is like this, at this time instant it is like this. Okay, it is directed in a particular way as shown in the diagram. Okay, so you can write in a more detailed form. LB will be equal to mass times L cross vector omega cross r, because we know velocity is expressed as omega cross r. Vectorially it is written. We usually write V is equal to r omega. In fact, that is not correct. We must write vector V equal to vector omega cross vector r. So if you take the vector direction, you can see from the diagram that LB is directed like this everywhere, because r is like this and velocity is tangential. So and omega is upward. So omega cross r, okay, omega cross r will be tangential to the radial path. Okay, that is V. And when you take the L cross V, you can see that it is always directed as shown in the figure. Okay, even here you can see it is directed in a particular way. So now we have both the angular momentum with respect to A and angular momentum with respect to B as shown in the figure. So we can add up it. So we will get the total angular momentum LA plus LB, that is given as mr square omega k cap plus m into vector L cross omega cross r vector r. So let's now take a little bit interest in the direction of vector LB. What is important in it, as I told you, these are the direction of vector LB. These are at two different time instant. The direction of LB is shown in the figure. And vector LB always have two components. One is vertically upward and one is radially outward. You can say radially outward. Vector LB has two components. One is vertically upward, one component, and radially outward. All the radially outward component will be mutually cancelled because they are mutually opposite, equivalent opposite each other. Everywhere it is opposite each other. But the vertical component, they exist. Okay, so here a cone is shown. Okay, this cone always shows the direction of angular momentum at a different dimension. Different dimension angular momentum is shown. So the vertical component LB will be added with the LA. LA is, as you know, LA is always directed upward. Similarly, vertical component of LB will be also added upward. Okay, as shown in the figure. So sum of the angular momentum will be like that. And LB is, as I told you, LB is changing every time. But LA is not changing. LA is always directed upward. Whereas LB is directed in different directions, different dimensions. And you can say LB sweeps out a cone as shown in the figure. Okay, LB is sweeping out a cone. If you compare all, if you displace all the LB component to upward, you will see that will trace out a cone. So LB makes out a cone in the space, whereas LA don't make, they get it always directed in a particular direction. And as I told you, LB component of Z component LB is a constant, whereas the horizontal component travels around the circle with the bob. So you can say horizontal LB changes with respect to time, whereas vertical component is invariant, it does not change. Okay, so what is the physics of that? We have LA and LB now. The physics of that is like this. We can explain like this: P naught tau, the torque acting on a system due to its angular momentum given by delta L by delta T, partial differential of angular momentum with respect to time. So in our case, first to take LA, it is a constant and it does not have any dependency with the time. So you can say if you differentiate the LA, you can say torque will be 0. Okay, so by virtue of LA, angular momentum with reference to A, there is no torque acting on the body. With reference to LA, there is no torque acting on the body. Whereas with respect to LB, there is a torque acting on the body because LB is changing with respect to time. So we can, one physics we get is because of the angular momentum LB, there is a torque on the body, and because of the angular momentum LA, there is no torque on the body. Okay, this kind of situation exists in particle motion when charged particle spins. And if it is placed in a magnetic field, this kind of force can arise and they can lead into complex on interesting motions, and that will give you interesting physics. But you will study more detail. Okay, and the physical significance is that due to the angular momentum LB, there is a net torque acting on the body. We have studied in law of conservation of angular momentum that if angular momentum is constant, the torque acting on the body is either 0. Okay, it is 0. A similar situation come here because of the LB, there is a non-zero torque acting on the body. Okay, so the body can get accelerated or any such thing can happen. So that is the conclusion of this discussion. And here now we have a simple problem based on your angular momentum. Your conical pendulum. Question goes like this: a small ball of mass small m is suspended from the string of a conical pendulum of length L, capital L. The ball revolves with a constant speed v in a horizontal circle of radius small r, as shown in the figure. Prove that the expression for the velocity is v equals root of L g sin theta tan theta. Okay, over here capital L, g, theta all have the usual meaning. Okay, as we discussed earlier. You can prove it because in the section 1 we have discussed the theory. Once again go to the theory. You can definitely do this problem in a simple manner. And many other problems are there that will be definitely presented in the Google Classroom. You can search it. You can try it upon it. So for the time being, hope the ideas are clear. You try to watch the video at least twice before doing the problems. Have a nice time. Thank you all of you.